Hi, this is Nasnidowski, and we're going through section by section, every section of this book, Monoidal Categories, by me from MIT Press. Okay, and today we're doing section 3.3, which is called Slices and Coslices. The slices you'll see, coslices is, as we said before, we have to deal with duality when we switch around the arrows. This is probably this is by far the shortest section in the book. It's a page and a half in the book, but it's needed and it's used, etc. So let me just tell you what slices and coslices are. They're ways of making the morphisms in the category. So we have objects in the category, we have morphisms. We have ways of making the morphisms in one category into the objects of another category. Okay, so and they show up quite often. But let's just go back and see what we did. Chapter 3 is all about the structures in a category. What type of structure does a category have? Not what it's made out of, but what type of things that it has. So 3.1, we talked all about products and coproducts. And we generalized 3.2 when we talked all about limits and colimits. Okay, and now we're in 3.3, which is just one other thing we have to know about categories, namely these slices and coslices. Mainly, they're ways of going from, again, the morphisms of one category become the objects of another category. Okay, so let's go through it. Okay, and the idea is as follows. Given a category A, okay, and one particular element in the category. So A is an element in that category. Okay, some object in the category. Then we can form I have to see how the slice goes. Slice small a. Okay, we can form another category and we write it like this. It's A, but we slash out this A. I'm sorry, I shouldn't have said slashed out. We slash this A. Okay, so now I got to tell you what this is. I got to tell you what the objects are, and I got to tell you what the morphisms. The objects are very simple. They're pairs where B is an object in here, and F is a morphism in here. Okay, and it goes from B to A. These are the objects in here. Main thing is, the morphisms in this category become the objects in here. So they're pairs of things. B is one object, and a morphism is like that. Now, the main point is that you could have different, you could have B, and then you could have, I don't know, H from B to A. Okay? Main point is they all have co-target A. Okay, so they're all things like that. Okay, great. So those are the objects in the category. Okay, and the morphisms in the category are as follows. Well, let's say we have two objects. We have an object here, B, with a morphism like that. And we have another object, B prime, with a morphism like that. We'll call that F prime. Then a morphism in this category is a map in this category, G, such that this commutes. Okay? G composed F prime is equal to F. Okay? This triangle commutes. And you might have another one. So here's another typical element in here. Okay, we'll call that F double prime. And then we're going to have a morphism from here to here. We'll call that G double prime. And the composition in this category is simply the composition like this. If this commutes and this commutes, then this whole thing will commute. So we might write that as, that's G single prime. G single. No. Like that. Okay? So that's a slice category. Okay, great. So let's look at some examples. Okay, so you have the category of sets. That's our favorite category. We spent a lot of time on the category of sets. And you have, here's a typical element of the category of sets, namely the real numbers. Okay, and so now you could talk about set slash R, the real numbers. And what's this? These are all, here's a typical set, here's the real numbers. Okay, and here's another set, and here's the real numbers. So these are all real numbered valued set functions. Okay, and we insist that the morphisms from here to here commute with these things. So this is a typical thing. It's used in analysis. It's used all over. You want this. This is the This is the category of real number valued sets. Very good. Next. Okay. Let's do another example. Okay. You have a partial order. Okay. And so what's that? That's a set with a transitive and reflexive partial order or pre-order. Well, it doesn't matter. Okay. But now pick a typical element here. I'm going to make a lowercase p. Okay. And now I'm going to look at p, capital P, comma, less than, slash, I always forget the way the slash goes, slash little element p. So this is an element in the partial order, and now we're looking at this. What will that be? Well, that will be p prime arrow p. In other words, small p. In other words, this is going to be an element with an arrow like that. Now, in this category, there's at most one arrow each way. This means that p prime is less than p. And we might have another one, p double prime, less than it, and we have this. Okay? So basically, in this pre-order, if we look at p, we're basically looking at all things that map to p. In other words, all things less than or equal to p. Okay? And we write that as p downward. Okay? That's a small p downward. In other words, it's the sub-partial order or pre-order. It's the sub-pre-order that has all the elements less than p. Okay? Can't get less than that. Can't get better than that. Okay? One abstract point is left as an exercise, but we'll do it anyways. It's not so hard. And the idea is as follows. Take a category A, take an element A, okay? And then the question is, what is the terminal object in this category? Okay, so let's think about it. So here's a typical element in the category. Okay, and so I want another object in here, this is the terminal object, such that any morphism, such that there's exactly one morphism from this object in the slice category to this object in the slice category. And what could that possibly be? Well, it has to be as follows. If you have a morphism here, the only thing that's going to make this commute is if this is an F and this is the identity. So the identity on A, which goes from A to A, is the terminal object in this thing. It's like the last thing. Okay, and that fits very nicely with the partial order. In other words, that little p, with looking at all things less than that little p, well, the terminal object is p. So that makes sense. Okay, great. So that's the slice category. Okay, and as we said many times, whenever we have a notion in categories, we switch around the arrows and we get a new notion, which is just as useful, usually. Okay, and that's called this coslice category. Let's talk about that. And the idea is as follows. Given a category A and an element A in there, okay, what we could talk about is the coslice category, A slash capital A. Okay, and what's this equal to? Well, the objects are pairs of elements. What are they? They're pairs of elements B, okay, and F from A to B. Okay, so in the slice category, the little a is the target of all the maps. And here we're going to have the source of all the maps. Okay, the first thing. So here's a typical element, A to B. Oops. Sorry. Hold on. Here's a typical element, A to B. Okay. Here's another typical element, f prime to b prime. And what does it mean, a morphism in this category? Well, it's a morphism like that, such that this commutes. So that's a coslice category. Okay. Okay, so we have three nice examples of these things. Let's go through them. Two nice examples, really. Okay, so one is as follows. Take your beloved category set. We love the category of set, okay, because we get a lot of intuition about it. Okay, and we take that set. That's a pretty stupid set. Doesn't matter. One element set, they're all the same. Okay, and we look at the coslice category like that. Okay, good. Now, what is a typical element? A typical element of this is going to be a set with a map into it. Okay, and another typical element is another set with a map going into this. So we might call this F, and we might call this F prime. Okay, and what does the morphism have to preserve? It means it's a function from one set to the other set, such that this point goes to the same point as this. We call that pointed. We call this function a function of sets that preserves the point. Okay, and the way to think of it is, here's your typical element S. It has a particular point which is picked out by this one element set. So we might call this F of star. Okay, and here's another set, S prime, and it has a special point which we might call F prime of S of the star. Okay, great. So here's a point and here's a point. And what's a function from these points? This is a function that takes every element in here, but we make one requirement. This element has to go to that point. So a point has to go to a point. Now, it could be that other points also go to that point. That doesn't bother us. Okay, many things can go to that point. But one thing we insist on is that element goes to that point. That's it. Okay, so this is called the category of pointed sets. Okay, so it's sets, but every set has a special extra element which we call its point. Okay, great. We could do the exact same thing for topological spaces, and this is used all over. Okay, these are called pointed topological spaces. Okay, typical elements are a topological space with a designated point. Okay, and again, you could have another topological space with another designated point. And the only thing you insist is that this point goes to that point continuously. Okay, one more example of a coslice category. Okay, and that is if you have a partial order or a pre-order, and you have an element of that partial order or pre-order, then you could talk about this. And what's a typical element? It's P arrow P prime, or P small p double prime. Okay, and what's this? What is this? Well, very simple. This is the set of all elements where P is less than it. Okay, so we write this as follows. It's those elements, P with an up arrow, those things greater than P. These are all things that are greater than P in this partial order. Okay, and for the same reason as we saw before, you can do it yourself. In fact, it's a thing. The identity is the initial object, not the terminal object, of P slash P. Okay, that's it. Okay, so that's what a slice is. That's what a coslice is. Okay, there are ways of endowing. Well, there are ways of getting from one structure getting another structure. There are ways of getting either more structure, so a pointed set, a pointed topological space, or a subset of the structure, or totally new structures, etc. Anyways, like I said, that's the world's shortest section in the book, but it's pleasurable. Okie doke.